Hello class, welcome back to our discussion about binary relational algebra operators. And during this lecture, we will be discussing join operations. Key concepts to pay attention to is the difference between inner and outer joins, and make sure that you understand the basic concept behind or underlying each type of join. Finally, we're going to conclude our discussion today by talking about join operators. The join operation or join operations are used to combine two tuples from relations into a single tuple when the join condition is met. In order to join two relations, they have to be join compatible. This means that the join operation must involve attributes which share the same domain. Usually that means that we're going to join on a foreign key to a primary key or a key to a candidate key. The resulting relation is going to have a number of attributes equal to the number of attributes in both relations. The number of tuples will be equal to the number of combinations of R and S that meet our join condition. And we're going to look at a number of examples for each type of join operation over the upcoming slides. And you may remember back in our discussion about Cartesian products is that we did a Cartesian product with a selection condition, and we said that it was equivalent to a join. And so this is true. And the primary difference between a join and Cartesian product is that with a join, only combinations of tuples that meet that condition, that join condition, will appear in the result. Whereas with Cartesian product, without a selection, all combinations are included. And so just returning to our C relation and D relation, remember it's courses and departments. The Cartesian product returns 72 tuples. It's just every single combination of tuple from the C relation and D relation. However, we could do a join on relation C and relation D, and this is much more useful. And here we begin to see the power of relational algebra, where we combine selection, projection, and a join to obtain our third relation. And in this example, we're saying that we want to project only C name, credit, D name, and college. So we're getting the name of the course, the credit type of that course, the department name, and the college in which the department resides, where credits are equal to G. And then we also want to do a join on the C department and C relation and D relation, where the department code in C is equal to the department code in D. And this third relation is the result of our join operation with a selection and projection. It has 6 rows and 4 columns. And those 4 columns correspond to the requirements we placed in our projection operation, and the credit, notice that credit is all G, and that's because those are the rows that meet our selection condition. And then in addition, we have joined those two relations on the decode attribute, And so the courses only include department name and college for which the decode are equal. Okay, so now that we have the basic idea of what a join is, we're going to look at some variations on join. So there are several types of join. There are equijoins, natural joins, theta joins, which are all types of inner joins. And then there are outer joins. So there are left outer joins, right outer joins, and a full outer join. And we're going to look at examples for each of these in the upcoming slides. So the first join that we're going to look at is the equijoin. The equijoin involves join conditions with equality comparisons only. What that means is that the value for the corresponding attributes must be equal to one another. The result of an equijoin includes all attributes from both relations participating in the join operation. So all attributes from both relations. That means that if an attribute is present in both relations, it will be duplicated. So let's look at our example. We have relation 1 and relation 2. And when we do an equijoin, the resulting relation is the fourth table there on the right, and we see that we joined on attribute 2 or A2 and A4. So we have CY, CY, and it is repeated because the joining attribute is Y. So since we've already looked at a basic example, now let's turn to a more practical or realistic example. And for this example, we're going to return to our C relation and D relation. And we're doing an equijoin where the D codes from each relation must be equal to one another. And the result of that equijoin operation is the relation shown below. And just observe that the D code attribute, because it is present in both relations, is duplicated during an equijoin. And it's more useful than the Cartesian product because it doesn't include every potential combination of rows. It only includes those that meet our join condition, namely that the D codes are equal. And so this relation shows essentially what department each course belongs to. So operations research is a course in the business college. Principles of IS is a course in the business college. Financial accounting is a course in the education college. And next we're going to look at natural joins. Natural joins are very similar to equijoins with the exception or with the difference that they do not include the second superfluous attribute. So that attribute on which that is duplicated is not duplicated in the resulting join. So looking at or returning to our very basic example, R1 and R2, when we do a join on Y, the resulting relation only has 3 attributes or columns rather than 4 columns. And similar to our equijoin example, we will use the C relation and D relation in order to demonstrate a natural join. And we're going to do the natural join on the D code attribute again. And as you can see, the resulting relation from a natural join gets rid of that repeated attribute. So in contrast to an equijoin where D code is repeated, a natural join eliminates the superfluous attribute. In this slide, it just highlights one of the weaknesses or criteria for natural joins, and that is that the attributes must have the same name in both relations. And in this case, it is D code. If the attribute name in the D relation were not D code and were something else like department code, then the natural join would not work. And at this point, many of you may realize that we've seen this result before. And as you can see, it is very similar to using a projection with a selection and a Cartesian product. And so as with many things that we learn in this class, or many things with databases, there's always, or almost always, more than one way to obtain the result, the same result. The last of the inner joins is the theta join. Theta joins do not involve equality, but inequality, and they occur less often in practical situations. So you'll probably use natural joins much more often than you will a theta join. And let's look at our basic example again. We have relation 1, relation 2, and we look at the product of R1 and R2. So we have AW and CY, BX and CY, and so forth. And the resulting relation includes all of those rows for which the A2 and A4 attribute are not equal. And for our more complex theta join example, we'll return to our C relation and D relation. And the result of the theta join from the previous slide is this unfortunate relation in which the D codes do not match.